This is Linked Data Engineering, lecture number 4, Querying RDF with Sparkle. In the last sections of the lecture you have learned how to query RDF databases with Sparkle. But how is an RDF database structured like? How is it constructed? What's an RDF database? How does this work? And this is something we want to look at in this section of the lecture. So how to store RDF data efficiently and how to access it on a Sparkle or a Sparkle endpoint, which has an RDF store under it. First idea you might come up with, of course, we can use existing relational database management systems. Databases are around for more than 40 years, so why not using RDF in relational database systems? A graph, of course, we know that, can be represented as a set of triples, S, P, O, subject, property, object, which means you have one huge table in a relational database management system, which could have 3 columns, subject, property, and object. So triples can simply be stored in a relational database management system. No problem. And of course, we can make use of 40 years of research and experience in the DB database community. Why not? So why should we come up with something new? So how does this then work? How could I implement Sparkle queries? How could I implement Sparkle query processing in a relational database management system? Of course, first of all, if I want to query Sparkle, I have to translate the Sparkle query to SQL, with which I access the relational database management system according to a given schema. Then, of course, I use the database management system to answer the SQL query, and in the end I, of course, have to re-transfer the SQL answer to the Sparkle answer. This would be the way for Sparkle processing. But what do I have to consider if I simply do this? Okay, there are of course alternatives how I can store triples in a relational database management system. And we want to talk about 4 alternatives here. So first of all, using monolithic triple storage tables, which means I have one huge table, subject, property, and object. And we want to compare this with the options of so-called property tables, where I somehow aggregate. I make clusters of several properties and put them into one table of subjects which have the same properties. So these would be property tables. Then I can also, for example, for each property make an own table. This would be a so-called vertically partitioned tabled RDBMS. And I can use a hexastore where I make sophisticated usage of indices. I will show you how this works. So first of all, let's have a look at the so-called monolithic triple storage. And we have an example here with professors and their affiliation and students and their affiliation and stuff like that. So the basic idea is we store all RDF triples in a single table. And of course then the performance that I achieve with a query usually depends on efficient indexing. It's quite obvious, it's easy to implement, and it works also for a huge number of properties if the indexes are chosen wisely, so according to your application. So it depends on what kind of index do you need. Do you need an index on the properties alone, or should it be properties first and then object? So it depends on what kind of queries you want to pose. And of course, if you want to perform, let's say, complex, sophisticated Sparkle queries, unfortunately, you have to perform lots of self-joins. And this, of course, degrades performance. That's the problem with that. But in principle, no problem. How does it work? So you see here in blue, for example, a Sparkle query. What we want to do here is we want to select the universities of, we should be a grad students, and we want to know from which university these grad students have their bachelor from. So we want to have the universities where our grad students have made their bachelor. That's the first select query in Sparkle. How do I translate this in a relational database management system and SQL or SQL query? What you see here, it translates into a join. So we have again in red here the select query, and from joins the table with itself. So first we have the triples table and we use it as T1 and the triples table as T2. Then let's see how we combine it. So first we say from T1, let's take property P should be type and the O should be grad student. So this is from the first graph pattern that you see here. And then we go on and say then from triples T2, we choose the property bachelors from, and we say that T1S, so the subject, which is the student, should be the same as T2S, which is the subject. So you see here, these are the different join conditions, and what you select is from T2, the second table in our join, the object which is here the same as the university we are looking at. And what you can see here, it's already quite obvious that there is a specific pattern, how you translate the graph patterns into the filter conditions, the where conditions, the where clauses of the relational database system, where you do then for each combination of two triple patterns a self-join. So this is quite clear. If you then have 8 triple patterns, for example, which are combined conjunctively, you would also have to have 8 self-joins in your relational database management system. And this, of course, could be rather slow and inefficient. So the idea is, how could I, or which tricks can I use to make this more efficient if I'm using a relational database management system? Okay, first thing, of course, if in the SPO table I'm using, let's say, complete URIs, I will have lots of redundancy. So for the entire DBpedia, I would have the same URI prefix that I use over and over again. So the first simple thing that is done is you are using an additional table, which is the so-called resource table. And you use this for indexing URIs and literals with a unique numerical identifier. And then in your triple table, you simply use this new numerical identifier for each RDF term in the dataset. And then, of course, if this is a numerical, then of course the triple table, the RDF triple table, becomes much smaller than before, because you only have once for every resource the index entry, and then you are using the short numerical identifier in your RDF table. And this, of course, is much improvement according to space efficiency that you have, or storage efficiency. Then, of course, we have learned that in Sparkle, or we can use, or in RDF, we can define different graphs. We can use various graphs, and we can make queries, Sparkle queries over several graphs. So therefore, what is done usually is the triple table is extended to a so-called quadruple table or quad table. And then the fourth column, which is here the first column, is used as an identifier for the graph in which the triple resides. So usually here in a quad table, for provenance, for versioning and stuff like that, you're using an extra column, and in this column you have an identifier for the graph you are working in. So what else could you do? Usually, of course, the triples that you store in your table, many of them belong probably to the same class. Therefore, they have identical, or let's say similar properties. Here in our table, for example, if you look at it, we had professors and we had students. And of course, the professors have several properties in common, and also the students have several properties in common. So what you could do is you could combine those triples which have common properties, and of course then similar subject, to so-called n-ary tables. So this is an aggregation for all the professors, and then you put in, for example, the type property, teacher of property, bachelor's from property, master's from property, PhD from property into the same table. And you do a table for students where you then have, for example, a property for the advisor, and whether it's a teaching assistant and what kind of courses the student takes. So this would be an aggregation. And of course, you can use this ID-based encoding for better efficiency. As you see, of course, then you will need much fewer joins. This is clear. But on the other hand, the problem problem is, of course, how do you combine these properties? So this clustering of properties is another problem which is quite complicated. So this is not necessarily straightforward. How do you do that? How do you automate that? This is another problem to do that. What is also nice, of course, if the data is nicely structured, you will end up with a complete relational database. But potentially, so you do not have necessarily for each property really an entry for each subject. Therefore, you will have, or you will end up with tables which contain lots of null values, which is also not very nice. And another major drawback is multi-valued properties are not really possible. So for example, just think of a student who is taking several courses or a professor who is teaching several courses. Then here, for example, you have a full professor who is teaching AI. If, for example, this professor would also teach semantic web classes, we should put both in there. So in this column, in this field. And this, of course, is a bit difficult. So this is not, of course, then you would violate the first rule of relational databases. So, because each entry should be somehow atomic. And then if you put 2 in there, it's not atomic anymore. So this is a problem to represent somehow multi-valued properties in exactly this way with property tables. But what you could do in that case, of course, you could introduce so-called vertically partitioned tables. What are vertically partitioned tables? What you do here is for each single property, you create a 2-column table which contains subjects and objects which are connected via exactly that property. So for example, we have here a type table, we have a bachelor's from table, we have a master's from table, and then you have the subjects and the objects which are connected via exactly that one and only property. And of course, you're using this ID-based encoding for more efficiency. The pro on that side, of course, with this one, of course, you can support multi-valued properties. So for example, if you look at, let's say, takes courses table here, you could give ID4 then several courses, which would mean you have several rows, several entries here in that table that ID4 takes databases, takes artificial intelligence, and takes, for example, also semantic web. Could be possible, and it's quite easy to implement. Then, of course, you do not have any nulls in the table. So simply because if the property is not used for a specific subject, you do not create a row for that. So no nulls in that table. You create less I/O with that. If you have read only the needed attributes, so this creates less I/O, it's clear. You do not have to perform a clustering, and it has an excellence performance if the number of properties is small. And of course, if the queries you are posing are queries with bounded properties. If you are querying with unbounded properties, so if you are querying where properties is a variable, then you have to access all tables. So you have to make a query over all the tables. You have to join all the tables, which in the end might be complicated and of course inefficient. Another con is, of course, inserts are expensive. Simply think of something where a new property comes up, then you have to create a new table for a simple insert. This also is a rather inefficient procedure. And if you have a large number of properties, we have said this, and you have queries with unbounded properties, you might end up also with bad performance. So these are the drawbacks of these vertically partitioned tables. What else is out there? So-called hexa stores, where you have indices for all combinations of subject, properties, and object, which means every possible combination, starting with the subject, starting with the properties, starting with the object. So it depends on what kind of triple patterns you are looking for and where the variables in the triple patterns are. You create a specific index. You can query, for example, over the properties, over the objects, over the subjects, and you create an index in each possible direction. And then you end up with triples, of course, with 6 potential available indices. What you do here for the most common index, SPO, if you start with a subject and ask then for properties and objects. Then for the subject key S1, this points to a sorted vector of property keys, and each property key is linked to a sorted list of object keys. And of course, these object keys are also shared with another index, for example, with the PSO index, which is the index which starts with a property, then the subject, and then the object. And of course, if you have indices for each possible, let's say, sequence, the nice thing is then, of course, you are able also to access the data rather fast and to perform the queries rather fast. I mean, the drawback, of course, is if you have nevertheless many self-joins, this might take time. Therefore, there are also other native implementations of triple stores which make use explicitly of the graph structure and which are then working, for example, like a graph database. So just look around, you will see lots of different implementations of triple stores. Before we come to an end, let's shortly have a look at the pros and cons of these hexa stores. Of course, now in the beginning you have fast joins, but the problem with hexa stores, you see this, you need additional indices, you need 5 times more storage. And of course, if you need so many storage, sometimes this does not fit into the memory and then you have to switch over to the disk, and disk I/O, of course, this is costly, this takes time, and therefore this might be then in the end an inefficient implementation. So this might be a drawback if your database becomes large. Here you have a list of triple stores that you can access, that you can try out. So there are native RDF triple stores. One example, the last one here, is BlazeGraph, which is quite easy to use, and we will use BlazeGraph then also later on in our examples. And there are, of course, RDF stores which are based on database management systems like Apache Jana SDB or the Oracle one, which of course relies on the Oracle database. And there are hybrid RDF stores which are mixtures between relational database systems, graph database system and stuff like that, like Sesame or OpenLink Virtuoso, which are also rather prominent triple stores. If you want to know what's out there, the W3C maintains a list of the available triple stores. Simply click on the link and then you will end up on the W3C list of available triple stores, and you can see what kind of openly available triple stores are there, and of course there are also commercial triple stores available. So far so good. So this is what I wanted to tell you about the possibility to store RDF data into databases. And what we want to do next, and this then is the last section in the course of Sparkle, I will show you that Sparkle is more than just a simple query language.